So let's look at this energy problem. I know how to solve this problem. I know how to do what we just did too. I've done it before. I did something wrong and I can't figure out what to do. Alrighty. So, I think part of the problem is, no, I'm not gonna spend more time thinking about it. All right. So here's the problem we're to look at. On a thrill ride, a cart is filled with people that have a mass of 1,000 kilograms. So we have this cart down here filled with people. It compresses a spring with a force constant of 45,000 newtons per meter by a distance of 2 meters. The spring pushes this cart up a 30-degree incline that ends abruptly 20 meters from where the cart is released. We want to find the distance up the plane the cart stops, or if it will go over the edge. Okay? So it's not shown here, but the idea is that there is some kind of a spring that's being compressed here. Let's go back to full screen. There's some kind of spring that's being compressed right here. And it's being compressed by an initial distance of 2 meters. And what we want to figure out is what's going to happen when this cart moves up the ramp. So we'll draw a second picture down here, probably using like something like this. And the final situation, what we're going to have is our spring is going to be kind of decompressed. And our cart is going to be somewhere up here. Now, it might actually fall off the ramp if it goes too far. But what we want to figure out is basically how far up the ramp does it go, okay? So it starts initially right here, and it's going to go some distance up the ramp. And that's what we want to calculate, is how far up the ramp it's going to go. And we're given a bunch of information here. All right. So let's just define that distance to be d, the distance that it actually travels. And that's going to be what we're solving for, is how far up the ramp does the cart actually go? All right. It's an energy problem, and the way we handle energy problems is we're going to be using our work energy equation. I don't think there's any friction in this problem. And if we expand out this equation, what it says is change in kinetic energy is 1/2 mass times V final squared minus V initial squared, plus change in potential energy is going to be the change in potential energy due to the spring, which is 1/2 kx squared. X final squared minus x initial squared. And then we also have to add in the change of potential energy due to gravity, which is going to be mg times y final minus y initial. Okay. So the key thing for solving energy problems is just identifying what all these variables are at the two different points that you've chosen. So we have the initial point right here, and we have the final point down here. So we just need to basically make a little table. What is x initial? What is y initial? What is v initial? And then down here, what is x final? What is y final? And what is v final? Okay. Now, since it says the cart starts off down here, what's the initial velocity of the cart going to be? Yep. And let's assume that the cart doesn't actually slide off the ramp. Now, we know the ramp is 20 meters long. So if we solve for d and it's greater than 20, then we're going to know that the cart's going to go over the ledge, right? So let's assume it doesn't go off the ramp. If it doesn't go off the ramp, what will v final be? Also 0. Yeah, that's great. Now, what we're choosing, let's do x's next. So x represents the compression of the spring, right? How much is the spring compressed in the initial situation? 2 meters. And how far is the spring compressed in the final situation? It's not d plus 2. The spring isn't really doing anything in the second part, right? It's no longer connected to this. It's not really storing any energy anymore. It's back to 0, yeah. Back to the equilibrium position. Now, the idea here is that if you call this x equal to 0 for the spring, we're back to x equal to 0 again. We're back to the equilibrium position for the spring. And more importantly, this block or whatever, it's not really attached to the spring anymore. The spring just isn't, it's kind of become separated from the system in a way. Between y initial and y final, we can always choose one to be 0. So let's choose this one to be 0. And what would y final be then? So I have an object. It moves up an inclined plane where we have an angle of 30 degrees right here. It starts at this point. It moves to this point. So this is y initial, which we're calling 0. This is going to be y final. Sorry about that. This is d. If you want to do that somewhere, that's fine. You can make this negative. It's not going to make any difference, but you can do it if you want to. Because you square it anyway, right? We're going to square it anyway, right, Summer? So all we really care about when we talk about this is how compressed the spring is. So it's like, we'll just call it positive 2. D sine 30, that's right. So y final then is going to be d sine 30, okay? Because basically you've got a triangle like that, like that. The angle is 30 degrees, and that's d. So this side over here is going to be d sine theta, or d sine 30. Everyone see that? Which is just d over 2, right? Because sine 30 is a half. All right, what's the work done by non-conservative forces in this problem? Are any of the forces acting non-conservative? Nope, no friction, there's no drag, nothing like that. So that's 0. So we get 0 equals all this stuff. This was 0. X final was 0. And y initial was 0. So we end up getting a negative 1/2 k times x initial squared plus mg times y final. And we can plug in our numbers now. So that'll be negative 1/2. Well, let's rearrange just a little bit. We're solving for d. So we're going to have 1/2 k x initial squared is equal to mg times y final, which is d over 2. We can solve for d, so we'll end up getting k x naught squared divided by mg should be equal to d, because the 2's cancel. So we're going to get k, which is 45,000 newtons per meter, times x initial, which is 2, divided by mg. The mass of the cart was 1,000. I'm just pulling all this stuff out of the problem itself here. And gravity is obviously 9.8. Squared. Thank you, Chris. Appreciate that. This is squared. So can anyone calculate this? So 45 times 4 is 180. It's going to be a little bit more than 18, something like 18.2 to 4 or something like that. Oh, it is 18.4. That's a good guess. I was just guessing. I knew it was 18, but I mean, just because you can look at the numbers. But all right. So the cart doesn't actually go over the edge. Anyway, any questions? Yeah, exactly. All right, so let's talk about power. And probably have time to do one power problem. So power is basically the rate at which energy is being done, or the rate at which work is done. It's the rate at which work is done or energy is used or consumed, basically. So there's really two different ways to write this. You can write the basically that power, we use the symbol P, should be equal to the work divided by the time interval over which the work is done. Okay? Or you can write it as power being equal to kind of the rate at which energy is changing, so like the change in mechanical energy divided by time. This could be kinetic energy or potential energy, basically. All right? And if we look at this particular definition right here, if we want to know what this would kind of be average power in both of these cases. So what does power mean? Power is basically like saying, let's say that I go buy a lawnmower, okay? And I take this lawnmower and I use it to like mow my lawn, okay? If somebody else, so let's say that I mow my lawn and it takes me an hour, for example, okay? Let's say that my neighbor goes and buys a better lawnmower, and they can mow their own lawn, which is the same size as mine, and it takes them half as much time. Then you might say that that lawnmower is twice as powerful because it can do twice as much work in the same amount of time, basically, or the same amount of work in half the time. Either way. So that's the idea of what power is. Okay. The units for this is basically the watt, and 1 watt is equal to 1 joule per second. But there are other versions of units for power. If you were to go and purchase like a lawnmower or a car, then the type of power that you're going to see when you purchase something like that, how is the power of a car usually measured? If you look at something like a Corvette, or its horsepower, right? So I believe 1 horsepower is equal to, I think it's 746 watts, I want to say. I don't know if that's right. Can anyone look that up for me? Is that right? And then, so what is a horsepower? Is it 0.746? Kilowatts, maybe? $746, okay. All right. Wait, someone said 7,460. Which one is it? Looks like it's 746. Okay. So what is a horsepower? So horsepower is measured in foot-pounds per second, I believe. And because nothing in the English system of units makes any sense at all, 1 horsepower corresponds to 550 foot times pound divided by seconds. For whatever reason. That's what 1 horsepower is. There's a kind of like, the idea of horsepower is it's kind of an old unit because it comes from the time when steam engines were first being developed. So the name of the unit for power comes from a person named James Watt. And James Watt is one of the people that developed some of the most, I think, commercially successful steam engines. I don't think he actually invented the steam engine. I just think he made a steam engine that could be sold to the masses. So when he was trying to sell these things to people, he was largely trying to sell them attached to machines, these steam engines, to help people like do farm work and stuff like that, because we had a much more agrarian society at the time. And a good way to sell a new machine to someone that's been using horses is to just say, well, this machine is the equivalent of like 10 horses, and then that might convince someone to buy whatever machine he was trying to sell. So that's the idea of where horsepower came from and why it has such a weird unit. I think it's 55. People should look this one up too. I may have gotten this. Maybe it's 55 foot-pounds per second. These things are all. What's up?
I think the average horse has around 15 horsepower.
Oh, is that right? It's actually 15 horsepower for 1 horse? Interesting.
Yeah.
That's very interesting. I never heard that before. What is, where are the units and stuff in this book? It's 550. Okay, thanks for looking that up. All right. Sometimes I don't know if you guys do this. I do all my lectures without notes. I'm just other than these problems and stuff that I pull in, I don't actually use any notes. I just do the lecture because I've been teaching this class long enough. But sometimes I make mistakes, like the beginning of class today. That's why mistakes like that happen, is because if I'm doing this spontaneously, then sometimes I'll make mistakes. But I think that for me personally, that's just kind of my. You like seeing? Oh, thanks, Alicia. I appreciate that. 746. Oh, there's another one which is BTU per hour. That's an interesting one. I like that one. The British thermal unit per hour. Lifting 75 kilograms for 1 meter. Okay, so yeah, that's right, Louis. That's what that would mean, right? It'd be the same thing as lifting 75 kilograms up 1 meter in a second. And that's a lot, actually, if you think about it. That's what 1 horsepower would be, right? 75 kilograms is about 150 pounds, right? More really, it's more like probably 170 pounds, something like that. So if you could lift 170 pounds a meter, which is pretty high, in 1 second, that's like 1 horsepower. That's a good way of putting it, Louis. I like that. Okay, so that's our definition of average power. If we want to do instantaneous power, we just kind of take the limit as delta t goes to 0. And for instantaneous power, what we'll say is basically that this is going to become the derivative of the work with respect to time. But then what we're going to do is we're going to take the integral that we used earlier that says that dw is basically equal to f dot ds or dr. And we're going to plug that in here to get a different definition of how we do instantaneous power. So this is if we replace the dw with f dot dr, then we can look at dr dt. What would this be equal to? R is like a position, and so dr dt would be the rate of change of the position of an object. So it's velocity. Yep. So then we can replace this with just the force dot product with the velocity. So that's another way to find instantaneous power. This is a pretty helpful version of the power. All right. Force times velocity. And I think that's enough for us to solve a few of these problems. So the rate at which energy is done, that's what power is, measured in watts. Anyone have any questions? All right, I got 2 problems here. And you'll see problems just like these on your homework. So I want to make sure that we cover them before you have to try to struggle with them. All right, so this problem says a car engine has an output power of 20 horsepower when the car is traveling at a constant 55 feet per second on a level road. We want to find the average drag force on this car and then do some other things. Let's start with that. All right, so we have an output power, I'll just call it power out, of 20 horsepower coming from our car engine. And it moves with a constant speed of 55 feet per second. So let's draw a picture of our car. It's cruising along the road with a constant speed. And if we wanted to identify the forces acting on this car, what would they be? So we'd have our normal force, we'd have our weight. We'd also have to have, because the first thing we're calculating is find the average drag force on this car, there's also going to have to be some kind of a drag force that points this way, right? And then in order for the car to actually move forwards now, there needs to be some kind of a forward force acting on the car, right? Now, in the problem, it says a car engine has an output power of 20 horsepower. So what I'm going to do is I'm just going to say there's another force that acts this way. And I'm just going to call that the force of the engine. So just consider this to be kind of like after all of the losses that exist within the system, this is the force that the car is actually outputting. Okay, this is just the engine's turning, and the turning of the engine will cause the wheels to turn, which then pushes off the road, and it makes the car go. And there's certainly going to be all kinds of losses and forces and stuff in there. But let's just sum all that up and say that's the force of the engine. And we'll basically say that the drag force is going to account for any loss of energy. So, those are all of our forces. If it's moving at a constant speed, what does that mean? Our goal is to figure out how big the drag force is, D, acting on the car. It's not accelerating, right? So that means that if I were to define this to be the x direction, I could say net force acting in the x direction would be equal to 0. There's two forces. There's the force of the engine minus the drag force is equal to 0. D is drag, in case that's not obvious. Drag is just the force of air resistance. This means that the force of the engine is equal to the drag force. So if we could figure out what the force of the engine was, we could figure out the drag force. So how can we do that? Well, we just said that one of the ways that you can calculate power is by taking the dot product of the force with the velocity. And we have power, and we have a force, and we have a velocity, so we can solve for the force of the engine. The force of the engine and the velocity are parallel to each other. So we could just write this as F times V. And we can solve for this by just saying power divided by velocity is going to be equal to the force of the engine. So this is going to be 20 horsepower divided by 55 feet per second. Now, you can't just divide 20 by 55. If we did that, we get a really tiny number, right? We get something that's like 0.4, a little bit smaller. So instead, what we have to do is we have to convert the horsepower to foot-pounds per second, so we can get the force of the engine in pounds. So if we take 20 horsepower and we multiply by, 1 horsepower is equal to 550 foot-pounds per second. Divide that by 55. Then we're going to get that the force of the engine is 200 pounds, I think. 2,000 pounds. $550 over 55 is going to be... No, it was 200, right? Yeah. I'm silly. I was thinking divide by 5. Okay, so if the force of the engine is 200 pounds, that's also what the drag force is then, right? Okay. Any questions? The next part says, if the drag force is proportional to the speed, and the speed doubles, find the power needed. Okay. So, I probably shouldn't have used up so much room here. What I'm going to do is just move this down, and we'll kind of start a new problem. So for part B, it tells us that the drag force is proportional to the speed. This is pretty consistent with the way drag works. So drag is proportional to the speed, right? When I have a proportionality like this, what I can do is I can turn it into an equation if I multiply the right-hand side by a constant. So we're just going to call this our drag constant, sometimes called the drag coefficient. Okay. Now it tells us the speed doubles, and our goal is to find the power needed to make the speed double, basically. So our velocity basically wants to go up to 110 feet per second now. So our goal is to find what is the power output of the engine at this point. Now we saw from before that the force of the engine ends up being equal to the drag force in this case. That means the force of our engine is also going to be equal to K times V. The output power of the car, we said, was equal to the force of the engine multiplied by its velocity. But the force of the engine is actually now equal to K times V. So this becomes K times V squared. So now we just need to solve this. But we need to find the drag constant. How could we do that? How can I figure out what that drag constant is? D review from the first question, exactly. So from the first question, we had drag was 200 pounds. And velocity was 55, right? So that means that K, which is equal to D over V, is equal to 200 over 55. So let's plug that into this equation. So K is 200 pounds divided by 55 feet per second. We multiply by our velocity squared. The velocity doubled, so it's now 110. Before I even calculate this, I want you all to make a prediction. What do you think is going to happen to the output power of the car? In order to double the speed, do you think we should double the power, quadruple the power, triple the power? What do you think we need to do? It's 4 times since V is squared. Conan is exactly right. That's right. Because the power is proportional to velocity squared. If the velocity doubles, the power has to go up by quadruple, right? So we could actually go back and we really could have done this problem without even doing all the calculations I did. I did the calculations because I wanted to show you there is a way to do it with calculations. You don't have to just do this. This equation, remember that I said that you could take a proportionality statement and you could make it into an equation by putting a constant in here, right? You can do the reverse. If I have an equation that's just a power equals a constant times velocity, well, that really just says that power is proportional to velocity squared, which means that if the velocity doubles, so you go to 2v, you end up getting 4v squared, which means you get 4 times the power, right? So our equation here should give us the same answer. We should get 80 out of this. But it's going to be in foot-pounds per second. So we have 200 times 110, which is 2 times this. So this is going to be, it looks like 800. Wait, 800? Wait a minute. That's what you get, right? Did I do something wrong? You get 44,000. Okay, thank you. Oh, I see why it is. Okay, no, I see what's going on. Yeah, 44,000. Thanks. I shouldn't try to do everything in my head. And the unit will be foot pound over second. And if we want to convert that to horsepower, then we basically just need to multiply this by the ratio of 550 foot-pounds is 1 horsepower. And so we get power out is equal to 44 is 4 times 11. This is 5 times 11. You get 800. I think you're supposed to get 80, though. Do you get 80? Yeah. There we go. So that's a pretty simple power problem. Oh. Well, I'll let you all solve the last part. It says, if the maximum engine output is 150 horsepower, find the maximum speed. You can just use this equation right here and solve for speed, basically.
Mr. Murdoch,
Yeah.
can you explain how you got 110 feet per second? And then can you explain about
It
that?
says in the problem, if the drag force is proportional to the speed and the speed doubles. When it says the speed doubles, that means that it goes to 110. What's your other question?
And then the red stuff next to it, can you explain how you got 2v squared?
The velocity doubles. It's the same answer.
My bad.
That's okay. Any other questions? Okie dokie. So I'm going to stop the recording.